Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where we talk about everything I want to, science and math. And today this is physical science, and we're talking about different families, different columns on the periodic table, and different areas of the periodic table and their characteristics. So first what we're going to talk about, well, first I want to show you this. I'll remind you of it. I talked about it last time, but on the periodic table, you have rows and columns, okay? So the columns are the ones that are the families, and they're more alike than the ones in the rows. The rows have some similarities, but by far it is the columns that have similarities, and they're called the family groups. And I showed you my book, People in My Family, my very scientific book, and that you see that the families have more in common than the representative members. These dads have more in common with their families, the monster family or the Muppet family, than they have in common with each other. They do have something in common with each other. They're both the biggest. They sort of have heavy eyebrows. But other than that, they look more like their families, okay? So that on our periodic table is the same way. Like if you looked at the things at the top of the periodic table, many of them are gases and they're small, but they still have more in common with their families than they do with the other gases that are the small elements up top. Now then, okay, so metals and nonmetals. So the metals on the periodic table, I probably should just keep this up here. The metals on the periodic table are from the, oops, I got it upside down. The metals from the periodic table are from the stair step over. The nonmetals are from the stair step over this way, and the ones at the stair step are called the metalloids. So what properties do metals have in common? Well, they're ductile and malleable. What does that mean? And ductile means you can draw it into wires. Malleable means you can hammer it into sheets. And they conduct electricity and heat well, and those are some of the properties of metals. A lot of them are shiny and pretty, and a lot of them are used for things like jewelry and nice stuff like that, and coins, fun things. The nonmetals are more brittle, brittle solids usually at room temperature. They don't conduct heat and electricity like metals do. They're not ductile, they're not malleable. And the metalloids are somewhere in between. These are the semiconductors, a lot of times, the things that conduct a little bit. And they used to not be so important, but now they're very important in the computer industry. Now then, how do these elements bond? Let me show you this. This is just part of the periodic table. And in it, you see these rings that represent the orbitals that the electrons are in. And if you notice, these family groups all have the same valence or outermost electrons. So they're all very similar. Now, it turns out that things from the left side of the periodic table tend to lose electrons. Things from the right side of the periodic table gain electrons. Then they have different charges, because remember, electrons are negative, and opposites attract. So there's a Paula Abdul song about that I could sing, but the opposites attract, the positive and negative attract, and they stick together in something called an ionic bond. And we're going to talk about that in the next chapter, I think, but very soon we're going to be talking about that. So that's how they bond, from something from one side of the periodic table to the other. Ones that are just non-metals bonding to each other, they don't transfer electrons, they share it, and it's called a covalent bond. And then there's another kind of bond called the metallic bond. And in it, these metals in that middle part of the periodic table, where there's things like gold and silver and platinum, things that you've heard of before, copper, nickel, iron, they do something called metallic bonding. And what this is instead of transferring the electrons from one atom to the other, or sharing it very neatly between two in a chemical covalent bond. What they do instead is they let their electrons just flow from one atom to another. And because of that, that's what makes them such good conductors of heat and electricity and shiny. I saw a thing once, all that glitters is not gold, but it has loose electrons. It's got flowy electrons. I know that's a science joke and it's pretty bad, but I have to say them anyway. All right, so metallic bonding, how I explain this is I say it's like parenting. That the elements that want to lose their electrons that are all the way over on this side of the periodic table, I say those are those bad parents who like leave their kids at Walmart, the parents who abandon their kids, because these elements over here want to get rid of their electrons. They just abandon their electrons. They lose them. These over here, I say, are the crazy parents who like go into the hospital and try to steal a baby. So these are the people who are child snatchers because they're trying to get a few more electrons, a few more babies. The ones in the middle right here, these nonmetals, what I say they do is they're the divorced parents. They have custody arrangements. They share the electrons between them, just like divorced parents. And just like divorced parents, usually it's not exactly equal. It's not like you stay with your mom on Monday, your dad on Tuesday, your mom on Wednesday, your dad on Thursday, is it? Usually one parent has more custody than the other, and that's the same way it is with these nonmetals, the way they share. Usually it is called electronegativity, and one of the elements can pull the electrons to itself with more strength, and they have the electron more. Like usually the mom has the kid more in the divorce, right? Not always, but sometimes. So that's how it is like with water. Water is oxygen, hydrogen. Even though hydrogen's over here, sometimes they put it over here right in the middle, and sometimes they put it over here. So hydrogen's kind of weird, but when oxygen, hydrogen share, making water, water gets in the water, it has a positive side and a negative side because oxygen holds that electron more tightly and it gets more, so it gives a negative charge on a little partial negative charge on the oxygen side and a positive partial positive charge on the hydrogen side, and that's why water is a sticky molecule and all those things I talked about last time. Now, so that's sort of how the bonding works, but with metallic bonding, the metals are more just, I say that they're like the hippies. When I was a kid in the 70s, a long time ago, there were these places where hippies would just live and they would let all their children run around and they would call all the men dad and all the women mom, and they would just run around wild, and they weren't really attached to any set of parents. And it was really idealized in the 70s, and you heard it in songs. There's one, it's called In Seattle, and it says, growing up like a child, beautiful, free, and wild in Seattle, born free. There were all these songs with this idea that children should not have a lot of rules. They should just be able to run wild and free like an animal until they get grown, and that was the ideal setting for child raising, including sort of like how lions are in a pride, just the cubs all running around. It was that idea. So that's what I say the metals are like, because they just let their electrons run around wherever they want to go, free and wild, flowing around, not attached to any element. So they're the hippies in the middle. And that's metallic bonding. Just letting these electrons flow wherever they want, which is great because it makes it where metals can conduct heat and electricity. And I like electricity, so I like this property of metals. It also makes them shiny. Now, the first column on the periodic table, the first family, is called the alkali metals, the first family. They are very reactive because they want to get rid, they have one electron in their valence, one valence electron in their outermost shell, and they want to get rid of it. So they're very reactive. They react with water, and they're just working hard to lose that electron. Why? Why do they want to? Because all the way on the other side of the periodic table, there's a family called the noble gases. The noble gases have full levels around their nucleus, full shells, full orbitals. and they are very stable. And that's what all the other elements want. They want to be stable. Now, I've had people say, what do you mean they want? Do they think? Do they have brains? No, it all has to do with energy. They're going to be more stable if they have full energy levels like the noble gases. So they do that by losing electrons, gaining electrons, sharing electrons, or letting electrons just flow around. But that gives them more stability. They're like a noble gas, and they're happy. So the alkali metals want to get rid of one electron. They're metals. Some of these are ones that are like important for life, like sodium. You need sodium in your diet. Hydrogens and water. You need water. Lithium is used. It's good for your brain. It's in, like, when people are depressed, sometimes they have to take lithium. And around here we have a town called Lithia Springs, named after lithium, and it was known even to the Native Americans before the coming of the white man that the water at Lithia Springs that has lithium in it, if you were sad, would make you happy again. And lithium's used as an antidepressant. So I think that's so cool, showing that how advanced the Native American societies were. And we have some great museums around here. We have one called the Etowah Indian Mounds, and they have just a great little museum where they show how the Native Americans traded all of these goods all over the Americas. It really had trade routes, and you know, the water from Lithia Springs could go to California to make somebody happy. They had trade routes for stuff like that, so it was really cool. So homeschool field trip, or just field trip you might want to go to. As you go down these families, these columns on the periodic table, the ones at the bottom are often radioactive. And we talked about last time how if they're too big, they've got too many neutrons, they become unstable, they give off radiation, alpha, beta, gamma particles, and other things. Positrons, and there's all kinds of cool stuff. The next little column is called the alkali earth metals. They're slightly less reactive, but they're beryllium, magnesium, calcium, more of those elements that you need for living. You know that you need calcium and some of those. So in our bodies, what are the living elements I call chnops? It's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those are the main elements that make you up. But there are 33 minerals and trace elements that you have to have some of for living. You know, of course, you have to have calcium. Your bones are made to have a lot of calcium in them. So like you need a lot of that, but you also need potassium, magnesium. You even need a tiny bit of arsenic. Isn't that weird? A lot of arsenic will kill you. It's the murder weapon on the periodic table. But you need just a tiny, tiny bit, which you get in your diet. You don't go take a arsenic supplement. That would kill you. All right. So then the periodic table goes down, and those are called transition elements. And those transition elements, the ones in the middle, are very stable. They're found uncombined in nature, so they're ancient metals. And a lot of times their symbol reflects their ancient name, where their name is their modern name. So in the middle you see gold with the symbol AU, silver with the symbol AG, lead with the symbol PB. Iron with the symbol Fe, where most of the elements have their name and their symbol are very similar. They're the first letter or the first couple of letters a lot of times. The ones in the middle are different, and it's because they are very stable, uncombined in nature. So you can find a hunk of gold. You can pan for gold and find uncombined gold. You can find silver uncombined. So you'll be reading more about these elements. The more you know about them, the easier it is to remember them. So where we get these metals from is we mine them out of the Earth's crust. And aluminum, a lot of these important metals. Now aluminum is not found uncombined. It is found in an ore. It's found as a mineral combined with other things. And that's how it was known for a long, long time, until finally a chemistry student figured out how to separate aluminum cheaply. And then at first they were like, oh, this is really great. And they made like aluminum crowns and aluminum silverware for fancy people. And then they realized they could do it cheaply. and then it became real cheap. So aluminum silverware, you don't want that. That's no good. You want good stuff like silver or stainless steel. But actually now they think that aluminum is bad for you, that it might contribute to brain problems like Alzheimer's. So now people are trying to get away from aluminum. Like you can buy aluminum with deodorants with no aluminum in it. People don't want to use aluminum bakeware anymore. They want to use stainless steel or copper or something like that, because there has been some indication, it's not proven, but some indication that there might be a connection with some of these aging, or not necessarily aging, but some brain problems might actually have, aluminum might be bad for your brain. So I'm trying to get rid of all my aluminum stuff. I still have a little bit of aluminum cookware. I have this cookie sheet that I really like, this aluminum, and I want to get rid of it. And I'm always looking for a better one, like a stainless steel one, but they're hard to find because aluminum's cheap and people want to use it. All right, so nonmetals, we talked about their properties. We talked about that hydrogen is over in the first column because it has one valence electron, but how it acts is like a nonmetal. So sometimes they'll put it high above the periodic table like an angel floating above the periodic table. And then sometimes they'll put it over with the nonmetals next to helium. And sometimes they'll draw it in all three places with little dotted lines between it, because in some ways it shouldn't be floating above the periodic table. It should be one or the other, but it really doesn't have the properties of a metal. It's not ductile. It's not malleable. It doesn't conduct electricity and heat. It's not shiny. It's a gas. So sometimes you think of it going over there more. So, but hydrogen is important. Now, the column right next to the noble gases is called the halogens. Halogen means salt former. So these are the things like salt. Table salt is sodium chloride. So chloride is a halogen. But there are other salts besides table salts. You know, there's Epsom salts and ice cream salts, and there's other kinds of salts out there. That's not the only one. And with those metals on the other side of the periodic table, they form ionic compounds, which are called salts. All of them, fluorine, chlorine, bromine, iodine, they all are disinfectants. So they're used to kill germs. You might have had an operation, they paint brown stuff on you before you have a operation that would have a halogen in it. Iodine, you might have that put on a sore. Chlorine is added to water, pools, and your drinking water to disinfect up fluorine. You disinfect your teeth with brushing your teeth. So they're all important disinfectants. They're salt formers, and they're used for a lot of things. Now, what are the noble gases used for? I told you that they're pretty inert. They don't do anything. They're used in signs. So when you see a neon sign, neon is a noble gas. If the neon sign is red, it's actually neon. If it's a different color, it is a different noble gas or mixture. So when these gases are charged with electricity, they glow, they give off a color, and that goes back to the video I told you to watch, Adam's Ring of Truth. It's on YouTube. It's an hour long, but well worth your time. In it, he explains about neon signs and about fireworks and about road flares and anything like that that gives off color. It's pretty interesting. Now, metalloids, I told you they're important for their semiconductors. And they've become more important. Now, what is an allotrope? An allotrope is where you have the same element, but it's bonded differently and it makes a different form. So the famous one is diamonds. I'm not wearing my diamond. My fingers don't fit it anymore, but I need to have it changed. But a diamond is carbon, and so is your pencil lead. Your pencil lead. It's not really lead, it's graphite. And here it doesn't have the bond, so it comes off in sheets. It's clay and carbon mixed. Soot is carbon not bonded to each other. They've discovered some new allotropes of carbon that's called Buckminster Fuller balls. It looks like a soccer ball, but they're called Bucky balls for short. And now they've discovered Bucky tubes. There's little tubes of carbon also they found in soot. So it's all carbon, but how it bonds completely changes its properties to be different and its value. Pencil lead is cheap, diamonds are expensive. So it changes its properties. A lot of these non-metal groups these families, their valence electrons are the same, but a lot of them are very different because a lot of them go from gas, sometimes to liquid, and then to solid, and that really changes a lot of their properties. Now, synthetic elements. What does synthetic mean? It means man-made. Uranium is the last naturally occurring element. Everything above that was man-made by atom smashers, taking little atoms and smashing them together and making a new element. Most of these don't live very long and aren't very important. They're fake. I don't even bother memorizing most of them because they're just fake. They live for nanoseconds and they're gone. They are not important. There are a few that have been used that stick around a little bit longer and have been used for things. So some of the ones that are closer to uranium, but especially these brand new ones that they've just made, they got names, they named them, they made them an atom smasher. They're not used for anything, and they're too unstable, and they're just not real. They're not important. So anyway, so that's it. That is the periodic table, a little bit about periodic trends. Come back next time and we'll talk about chemical bonds. Science is great. Like, share, subscribe.